That should be on now. And let's set up to look at the PowerPoints. Okay. Now, this the PowerPoint is showing in the large section of the screen. And then there's that little section that if we do anything where I need to have like a whiteboard, I'll come over there. But for right now, let's look at our PowerPoint lesson for today. It's segment 14. We are looking at internal energy. One of the key features and important things about all of the thermodynamics stuff that we do is what we mean by state functions. And state functions are those things that just depend on the initial state and the final state, and not how you get from one to the other. So we're going to look at internal energy now. And to do that, we have to think about what work is and what heat is, because these are the things that contribute to the internal energy in any kind of system. So when we are looking at the internal energy, we're going to be looking at the work. And work is the energy that you expend when an object is moved against a resisting force. So that's really important. The definition is work is minus F times dL. Now, or delta L, the change in the length or distance that we move something when we apply a force to it. Now, there's an important point because it is the resisting force. That's the reason for this negative sign here. If I wanted to move something to the right, and that represented a positive direction, the force that is opposing me is the opposite direction. So the force and delta L will have opposite signs. So I need a negative sign outside here in order to make the work have the correct sign. Now, a system can possess energy if it can do work or transfer heat. And energy by virtue of motion is called kinetic energy. Okay, we missed a couple of slides. I wanted to illustrate the concept of work. Here's a little guy that can apply this small amount of green amount of force pushing on this big box. But the friction on the box on the table is much, much larger. So he can push as hard as he wishes. As long as his force is less than the opposing force, then no work is done because he didn't move something. Now, that is critical to work. If you look at a system in the beginning, the starting conditions, and look at it at the end, if a boundary hasn't moved, no work is done. So no matter how much force you apply, if you don't move the object, if you don't move a boundary, then no work is being done. So this little guy is not able to do any work against an object that can oppose with a force greater than his own. Now here's the same little guy, but now he's got a little box. And the little box, he can still apply the same amount of force against that little box, but the little box force resisting him is smaller than what he's applied. So if we watch this one, the little guy is able to move the box across. So the distance, he did move the box against a force, so the work is not zero because the change in length was not zero. So if you see a boundary move, work probably was done. So in this case, the work wasn't zero. but in the other case it was. So remember, the amount of work you do is not determined by the amount of force you apply, but by the amount of force that's opposing you. That's why we can move the several ton Hubble telescope out in space. They had to go up there and move it around and do some stuff to it. And one astronaut could easily do that because the force of resistance, gravitational force out there was extremely low. And so he was able to move that object easily. So as long as you can apply more force than is resisting, work will be done. But the amount of work that is done is determined by the resisting force, not by your force. If you apply force that's in excess of the resisting force, the object will not only just move, it will accelerate. That's Newton's second law of motion. Net force is equal mass times acceleration. Acceleration is how fast the velocity changes. So it not only moves, it gets faster and faster and faster as long as you apply a force exceeding the resisting force. So work is the resisting force times the change in movement. And as I said a while ago, the resisting force and the direction we count as positive are in opposite directions. So we want positive work to be done, and so we need that negative sign out there. Okay? Yeah. Now, a system that has energy, if it can do work or transfer heat, those are the two ways we're going to look at energy. Now, energy by virtue of motion is called kinetic energy. Kinetic energy is defined as 1/2 mv squared. Now, just to get our units straight, let's understand. Mass has to be in kilograms. That's the SI unit for mass. It's kilograms, not grams. Velocity is distance over time, and distance has to be meters. So the energy unit is 1/2. The unit's going to be kilograms, meters squared per second squared. And that we're calling joules. Now, potential energy is another type of energy that a system could possess. It can have energy because of its position or composition. A rock on top of a hill has more energy than it has in the valley. A balloon containing methane and oxygen has more energy than it will have if the methane and oxygen is converted to carbon dioxide and water. So the composition of a system determines its potential energy as well as position in a gravitational field. Now, thermal energy is energy transferred from a hot object to a colder object. Now, that's the way it always flows. You never see heat go from a cold object by itself into one that's warmer. It always goes the other way. Now, let's look at temperature and see what it really is. It's a measure of the amount of energy that is possessed by the components that make it up. Let's look at a little more detail. Here's an experiment that really does happen. If I'm lying, I'm dying. This is true. If you put nitrogen at 1 atmosphere pressure, add one atmosphere pressure diatomic nitrogen, you say the temperature of this sample is 25 degrees. Now, focus on, there's a little tiny hole between the chamber that contains the nitrogen and the other chamber, which is a vacuum. Now, you know what's going to happen. The gas is going to flow through that little hole and come out over here into this other region. And if we measured the temperature way over here, far away from the hole, you measure 25 degrees. Now, did that surprise anybody? I don't think so. That's what you'd expect. This will surprise you. If you measure the temperature of the gas that just as it gets through that hole, the best we've been able to reach is 2 degrees above absolute zero. So the temperature right there by that hole is almost absolute zero. Now, I would ask you, what cooled the gas in going from this side at 25 degrees to just going through that hole all the way down? It cooled it all the way down to 2 degrees Kelvin. What did that? It's a trick question. Nothing did. But it did happen. What heated it up from 2 degrees Kelvin to 25 degrees Celsius, 298 Kelvin, just by going across to the other side of the chamber? Why does this happen? Well, let's look at things on a molecular level, and then it will make sense. In the gas at 25 degrees, we've got lots of different molecules traveling at lots of different speeds in lots of different directions. So the length of the arrow is to represent the speed of the molecule, and the direction is showing where the direction is, where it's going. And you can see there's a disorder, completely random distribution over here of molecular speeds and directions. Now, so you got random molecular motions. Which molecules are able to get out? Only the ones that just happen to be headed toward that hole. Of all of that random collection, there was a few molecules going straight for the hole. Those are the ones that escape. Now, when you take away that randomness, then you wind up with a temperature near absolute zero. In fact, if you took all of the randomness of the velocity away, the temperature would have been absolute zero. Our best experiment gets down to about 2 degrees Kelvin. Now, why do you get 25 degrees again way over here? Well, let's look at that molecule now that's just coming through the hole. It's traveling faster than the ones that are already got out. So eventually it's going to overtake it. It's going to hit it. It's going to hit near the top or the bottom or the left or the right. We don't know where it's going to hit. So it's going to hit at some direction and bounce off away from that. And so the two molecules after the collision will move away from each other. They'll create more possible collisions. And the next thing you know, you're out here. You have a random pattern over far away from the hole that pretty well matches the random pattern that you had before. So the temperature is the same. Now, that's temperature is a measure of hotness, but the number increases as you increase the randomness of the motion of molecules. So it's the randomness and the motion of the molecules that cause the particles to have a zero temperature or near absolute zero temperature. So to sum up, temperature is only defined for a collection of particles. A single molecule doesn't have a temperature, because if I know where it is now and how fast it's going, if it doesn't encounter anything else, I can tell where it is 1,000 years from now or 1,000,000 years from now. It wouldn't matter. There's no uncertainty into where it's going. So, and I can predict exactly. So there's no randomness for a single particle. Now, if I put two particles together, could be some randomness, but I can still keep track of it. I can tell whether they're on a path that will ever intersect. And from physics, I could calculate if they are on a path that will intersect. I can calculate when that will happen and where in space that will happen. So again, it's not uncertainty. It's not random. I can still predict exactly the position. So if I get several molecules like a mole, I've got 6.02 times 10 to the 23rd particles in that sample. There is no way that me or even the biggest supercomputer in the world could ever predict where all those particles would be at some later time. So the temperature is certainly well defined for a mole. It's not defined when you get to smaller amounts. Where does that crossover occur? I don't know. but I know it's any amount of sample that I can actually measure in the lab, weigh it in the lab. It's going to have a defined temperature because the number of particles present is going to be so huge and so immense that even the slightest uncertainty in the direction molecules have when they hit each other will produce randomness in the sample that can't be accounted for. So at high temperature results from randomness in the translational motion of the atoms and molecules that make up a sample. Molecules of a hot sample are moving at a higher average kinetic energy, but that isn't the temperature. The randomness is what's determining the temperature. Now, the average kinetic energy turns out to be very, very simple. It's just 3/2 times R times T. Now, R here has the value 8.314. It's the ideal gas constant, but it's in the units is 8.314 joules per mole per Kelvin. And the temperature has to be in Kelvin degrees. So if you tell me what the temperature is, I can give you the average kinetic energy of the molecules that make up that substance. And by the way, the books don't tell you this. They imply that this is just gases. It is not. It's independent of substance or phase. Anything at the same temperature, no matter whether it's a solid at that temperature or a liquid at that temperature or a gas at that temperature, it has the same average kinetic energy. 3/2 RT. The only difference is how far the molecules move before they collide with something else. In gases, they move great distances before they collide with another molecule or with a container wall. Many, many, many billions and billions of molecular diameters they travel before they hit anything. If I'm talking about a liquid, the molecules are, you can think of it like the molecules are moving within a cage. They're bouncing around, bumping into other molecules, but all the time they're bouncing around in there, their average kinetic energy is still the same. Now, in the liquid phase, they have enough kinetic energy that that molecule can move out of the cage it's now in into the next adjacent cage of other molecules. And so you can have diffusion of molecules in the liquid phase, but it's rather slow. But at any moment of time, the average kinetic energy is still 3/2 RT. In the solid phase, the particles are all clamped into one particular cavity. That molecule never gets out of that cavity. It bounces around within the cavity, but it doesn't have enough energy to move to an adjacent cavity. But its average kinetic energy is still 3/2 RT. So that's something you probably didn't know, and I hope you do learn something at every lecture, but I bet you didn't know that. SI units is joules, and I told you a while ago, from Newton's second law, it's mass times velocity squared. So it's kilograms meters squared per second squared. So that's the units that we have for that. So I think this might be a good place for us to end this part of the lecture. We're already a little bit over. And so I'll pick this up a little bit later. I see some of you stayed around with me, and I appreciate you doing that. I will now end this meeting and transcribe this much of the recording and put it up for you on D2L so that you can review it when you need to. And the rest of the people in the class who had to leave, they can go and review it there as well. Okay, so I'm going to end the recording now, and